Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be tackling a practice problem set that relates to our lecture on circuits. Let's go ahead and get started with problem number 1. Problem number 1 says, if a defibrillator passes 15 amperes of current through a patient's body for 0.1 seconds, how much charge goes through the patient's skin? In order to solve this problem, we need to understand the relationship between current, time, and charge. Electrical current is defined as charge flow, or in mathematical terms, charge transferred per unit time. So we can write this as I, current, is equal to Q, charge, divided by delta T, which is change in time. Now here, our ultimate goal is to calculate the charge given the current and the time. So let's rearrange this equation to solve for Q. Q is going to be equal to I multiplied by delta T. We're given the current, that's equal to 15 amperes, and we're given the time, 0.1 seconds. 15 multiplied by 0.1 is equal to 1.5. And here we have ampere multiplied by seconds. Ampere is coulomb per second, and this is multiplied by seconds. The seconds cancel out, and our answer is going to have units of coulombs. So the amount of charge that goes through the patient's skin, that's going to be equal to 1.5 coulombs. And that means the correct answer for problem 1 is going to be answer choice B. Let's move on to problem 2. Problem 2 says, a student places an ammeter with negligible resistance in parallel with a resistor to determine the amount of current that passes through the resistor. Does the student obtain an accurate reading? A says yes, because the student used an ammeter with a negligible resistance. B says yes, because the current going through parallel paths is equal. C says no, because the ammeter should have infinite resistance. And D says no, because an ammeter in parallel changes the current through the resistor. Now, an ammeter is an instrument that's used to measure the amount of electric current passing through a circuit. To measure current accurately, the ammeter needs to be connected in a way that ensures it doesn't disturb the flow of current. Normally, ammeters are designed with negligible resistance, meaning they introduce very little opposition to the current. And this design is intentional because if the ammeter had significant resistance, it would alter the current passing through the circuit, leading to inaccurate measurements. However, an important rule to remember is that ammeters should be connected in series with the component through which the current is being measured. In a series connection, the current only has one path to follow. So the entire current flows through both the ammeter and the component, in this case, the resistor. This ensures that the ammeter measures the exact current that is flowing through the resistor without any interference. In this problem, though, the student placed the ammeter in parallel with the resistor. This introduces a major issue. In a parallel connection, the current splits between the different branches. And since the ammeter has negligible resistance, most of the current is going to flow through the ammeter instead of the resistor. So as a result, the current measured by the ammeter will not reflect the actual current through the resistor. In fact, the presence of the ammeter will significantly change the way current flows in the circuit, meaning the reading is going to be inaccurate. So to summarize, the student's method is flawed because placing an ammeter in parallel with the resistor changes the current distribution in the circuit. The correct approach would have been to connect the ammeter in series with the resistor. So the correct answer to this problem is going to be answer choice D. No, because an ammeter in parallel changes the current through the resistor. Beautiful. Let's move on to problem 3. Problem 3 says the resistance of two conductors of equal cross-sectional area and equal lengths are compared, and they're found to be in the ratio 1:2. The resistivities of the materials from which they are constructed must therefore be in what ratio? In order to answer this problem, we need to know the relationship between resistance, resistivity, length, and cross-sectional area. And we can get this relationship from the following equation. R, or the resistance, is equal to rho, which is the resistivity of the material, multiplied by L, which is the length of the conductor, and this is divided by A, which is the cross-sectional area. Now, the resistivity, this is a property that's specific to the material, and it reflects how strongly the material opposes the flow of electric current. Materials with high resistivity, like rubber, make it harder for current to flow, while materials with low resistivity, like copper, allow current to pass more easily. Now, if the two conductors in this problem have equal lengths and equal cross-sectional areas, then those variables cancel out when we compare their resistances. This leaves us with a really simple relationship where the resistance is directly proportional to the resistivity of the material. In other words, the ratio of the resistance for conductor 1 to resistance of conductor 2, this is going to be equal to the ratio of the resistivity of conductor 1 to the resistivity of conductor 2. And since we know this ratio to be 1:2, we therefore know that this ratio is also 1:2. And that means that the correct answer for problem 3 is going to be answer choice B. Let's tackle problem 4. Problem 4 says a voltaic cell provides a current of 0.5 ampere when in a circuit with a 3 ohm resistor. If the internal resistance of the cell is 0.1, what is the voltage across the terminals of the battery when there is no current flowing? Let's start with some background information. A voltaic cell or battery provides electrical energy by driving a current through a circuit. When a battery powers a circuit, the measured voltage across its terminals is not always equal to the battery's true voltage, also known as the electromotive force or EMF. This difference happens because real batteries have something called internal resistance. The internal resistance of a battery is the resistance within the cell itself, which opposes the flow of current and causes some energy loss inside the battery. As a result, when the battery is actively delivering current, part of the voltage is lost across this internal resistance, and the voltage available across the terminals becomes slightly lower than the EMF of the battery. Now, to find the voltage across the battery terminals with no current flowing, we need to determine first the EMF of the battery. And we're going to use the following equation to do that. This equation says that V, which is the terminal voltage, this is the voltage we observe across the battery when current flows. This is equal to epsilon, which is the EMF of the battery, minus I, which is the current, multiplied by internal resistance. Now we want to solve for this variable right here, so let's rewrite this equation to solve for the EMF. The EMF is equal to V plus I R internal. Now we know these two variables, I is the current, and we're told that the current is equal to 0.5 amperes. And we're also given the internal resistance. This is equal to 0.1 ohms. What we really need to figure out is this V term. So here we need to calculate the voltage across the battery when the current is flowing. And for this, we can use Ohm's law, which says that V is equal to I multiplied by R. The current is equal to 0.5 amperes, and the resistance is going to be equal to 3 ohms. We're also given that in the problem. This gives us our voltage across the battery when the current is flowing, and it's going to be equal to 1.5 volts. So we can go ahead and plug this into our equation. Our EMF is going to be equal to 1.5 volts plus our current, which is 0.5 amperes, multiplied by our internal resistance, which is equal to 0.1 ohms. This is going to be equal to 1.5 volts plus this is 0.05 volts, and that gives us a total of 1.55 volts. So the voltage across the terminals of the battery when there is no current flowing, that's going to be equal to 1.55 volts, which is answer choice D. Awesome. Let's do problem 5. Problem 5 says, a transformer is a device that takes an input voltage and produces an output voltage that can be either larger or smaller than the input, depending on the transformer design. Although the voltage is changed by the transformer design, energy is not, so the input power equals the output power. A particular transformer produces an output voltage that is 300% of the input voltage. What is the ratio of the output current to the input current? So the key idea behind a transformer is that while it changes the voltage, it does not create or lose energy, assuming an ideal transformer. This means that the power going into the transformer is equal to the power coming out. Power in electrical circuits is given by the product of voltage and current, and we can use this equation to rewrite this relationship. The input voltage multiplied by the input current is equal to the output voltage multiplied by the output current. In this problem, the transformer is said to increase the output voltage to 300% of the input voltage. This means that the output voltage is 3 times the input voltage, and we can write it in this way. V out is equal to 3 multiplied by the input voltage. Since power remains constant, the increase in voltage must result in a corresponding decrease in current on the output side. Remember, these have to be equal to each other. And if we define V out as 3 multiplied by the input voltage, there needs to be a change that happens in the current output that allows this relationship to remain true. And for that to be the case, the output current has to be equal to the input current divided by 3. This tells us that the output current will be 1/3 of the input current. Therefore, the ratio of the output current to the input current is going to be a ratio of 1 to 3, and the correct answer here is going to be answer choice A. Yay, onward to problem 6. Problem 6 says, given that R1 is equal to 20, R2 is equal to 4, R3 is equal to R4, which is equal to 32, R5 is equal to 15, and R6 is equal to 5 ohms, what is the total resistance in the setup shown below? Now, the fastest way to tackle these kinds of questions is really just to simplify the circuit bit by bit. For example, notice that R3 and R4 are in parallel with each other, and they are in series with R2. Similarly, R5 and R6 are in series. If we determine the total resistance in this branch and in this branch, then what we're going to have is a total of 3 branches that are in parallel, and from there we can calculate the total resistance. To start, let's work on this middle branch first, specifically on R3 and R4. They are in parallel with each other, so 1 over the total resistance of 3 plus 4 is equal to 1 over R3 plus 1 over R4. This is equal to 1 over 32 plus 1 over 32. That gives us 2 over 32, and that simplifies to 1 over 16. Now we can take the reciprocal of both sides, and we get that the total resistance between 3 and 4, that's equal to 16 ohms. Then we can move on to the next step for this middle branch, and we can figure out the total resistance between R2 and R3, 4. They are in series. So the total resistance of 2 plus 3 plus 4 is going to equal a simple sum of R2, which is equal to 4 ohms, plus what we just figured out for R3 and R4, and that's 16 ohms. This gives us a total resistance for this middle branch that's equal to 20 ohms. Now we can move to this branch right here, R5 and R6. They are in series with each other, so the total resistance between 5 and 6 is going to equal the resistance of R5 plus the resistance of R6. This is 15 plus 5, which gives us 20 ohms. So this branch also has a total resistance of 20 ohms. And then in this branch right here, we only have one resistor with a resistance of 20 ohms. So now we have these 3 branches in parallel, and each branch has a resistance of 20 ohms. We can go ahead and figure out the total resistance in this setup. 1 over R total is equal to 1 over R1 plus 1 over R2 plus 3 plus 4 plus 1 over R5 plus 6. This is equal to 1 over 20 plus 1 over 20 plus 1 over 20, which gets us 3 over 20. Remember, this is equal to 1 over the total resistance. So we want to take the reciprocal of both sides of this expression, and we're going to get that the total resistance is equal to 20 divided by 3, which is approximately equal to 6.67 ohms. And that best aligns with answer choice B. So the correct answer for problem 6 is B. Let's move on to problem 7. Problem 7 says, how many moles of electrons pass through a circuit containing a 100-volt battery and a 2-ohm resistor over a period of 10 seconds? And here we're given Faraday's constant. Now, the first thing we need to do is we need to determine how much current flows through the circuit. And we can use Ohm's law for this because Ohm's law gives us the relationship between voltage, resistance, and current. It tells us that current is equal to voltage divided by resistance. We're given the voltage, 100 volts, and we're given the resistance. So we can go ahead and plug them in, and we have 100 volts divided by 2 ohms. And this gives us a current that is equal to 50 amperes. Now that we know that the current is 50 amperes, we can go ahead and move into the next step, which is calculating the total charge that passes through the circuit. We know that current is the rate at which charge flows through the circuit, and that's given by this equation, I is equal to Q divided by T. Now we're trying to solve for Q, so we're going to rearrange this equation. Q, charge, is equal to current multiplied by time. We have both of these variables. Current we calculated to be 50 amperes, time is 10 seconds. This gives us a charge of 500 coulombs. So a total of 500 coulombs of charge flows through the circuit over 10 seconds. Now all we have to do is convert the total charge to moles of electrons. We know the total charge. We can use Faraday's constant to determine how many moles of electrons correspond to 500 coulombs of charge. Faraday's constant tells us that 1 mole of electrons carries 9.65 times 10 to the 4 coulombs of charge. I'm going to go ahead and round this value to 10 to the 5, and then I'm going to take what we calculated for charge, 500 coulombs, and I'm going to multiply it by our conversion factor. 1 mole of electrons is equal to 10 to the 5 coulombs. And this gives us our number of electrons, which is equal to 5 times 10 to the negative 3. The answer that best aligns with this is going to be answer choice A. So the correct answer for 7 is A. Awesome, let's go ahead and jump into problem 8. Problem 8 says, in the circuit below, what is the voltage drop across the 2/3 ohm resistor? Now, the first thing I want to do is I'm going to assign each of these resistors a classification. So this is R1, this is R2, and this is R3. And what we notice here is that R2 and R3 are in parallel with each other, and they are in series with R1. And this is important because to determine the voltage drop across the R3 resistor, we need to start by calculating the total resistance in the circuit. For the resistors in parallel, the equivalent resistance is going to be written in this form. 1 over the resistance for this parallel circuit is equal to 1 over R2 plus 1 over R3. And that is equal to 1 over 2 plus 1 over 2 divided by 3, which we can rewrite as 1 over 2 plus 3 over 2. That's equal to 4 over 2, which simplifies to just 2. So 1 over the resistance of 2 plus 3 is equal to 2. Then we have to take the reciprocal of both sides of this expression to get that R2 plus 3 is equal to 1/2 ohms. Now we can move into calculating the total resistance. The total resistance in the circuit is the sum of the remaining resistor, R1, and the equivalent resistance of the other two. So that's going to be equal to 1/2 plus what we just calculated, 1/2. And this gets us a total resistance of 1 ohm. Now that we have the equivalent resistance, we can go ahead and calculate the total current using Ohm's law. Current is equal to the voltage divided by the resistance. The voltage is equal to 10 volts, and the resistance we just calculated to be equal to 1 ohm. This gives us a current that is equal to 10 amperes. Finally, with this knowledge, we can determine the voltage drop across the parallel resistors. Now, the voltage drop across R1, this is going to be equal to the current multiplied by the resistance. The current is 10 amperes and the resistance is 1/2, and that gives us 5 volts. So the voltage drop across R1 is equal to 5 volts. Therefore, there must be a 5-volt drop across both of these two resistors, R2 and R3, based off of what we know about Kirchhoff's loop rule. And that means the correct answer for problem 8 is answer choice C. Let's move on to problem 9. Problem 9 says if the area of a capacitor's plates is doubled while the distance between them is cut in half, how will the final capacitance compare to the original capacitance? Now, the capacitance of a parallel plate capacitor is determined by the following equation. This equation says that capacitance is equal to epsilon naught, which is the permittivity of free space, multiplied by A, which is the area of one of the capacitor's plates, divided by D, which is the distance between the two plates. This equation tells us that the capacitance is directly proportional to the area of the plates. A larger plate area allows more charge to accumulate, increasing the capacitance. The capacitance is also inversely proportional to the distance between the plates. A smaller separation between the plates makes it easier for charges to attract across the gap, increasing capacitance. Now that we understand the equation, let's carefully apply the changes that are described in the problem. The first change is that we are doubling the area of the plates. So if the original area of the plate was A, the new area becomes 2A. Since capacitance is directly proportional to area, doubling the area will double the capacitance. But that's not the only thing we change. We also change the distance between the plates. That distance is cut in half. So if the original distance was D, the new distance is D divided by 2. Since capacitance is inversely proportional to the distance, cutting the distance in half is going to double the capacitance. And so now we can combine the effects. Doubling the area increases the capacitance by a factor of 2, and cutting the distance in half also increases the capacitance by 2. And so the two changes multiply together to give us a difference of 4. The final capacitance is 4 times the original capacitance. And so the correct answer is going to be answer choice D. You can also see this if you go ahead and plug in the new values. Epsilon naught is multiplied by the new area 2A, and it's divided by the new distance D divided by 2. This can alternatively be written as epsilon naught multiplied by area divided by D. We're going to take these constants out, and that's a constant of 4. So we have 4 multiplied by our original capacitance. So the final capacitance is 4 multiplied by the original capacitance, and the correct answer for problem 9 is D. Let's tackle problem 10 next. Problem 10 says the energy stored in a fully charged capacitor is given by this equation, U equals 1/2 CV squared, where C is your capacitance, V is your voltage. In a typical cardiac defibrillator, a capacitor charged to 7,500 volts has a stored energy of 400 joules. Based on this information, what is the charge on the capacitor in the cardiac defibrillator? Now, the equation we're given in this problem is U is equal to 1/2 CV squared. U is our stored energy, and we're given that value to be equal to 400 joules. V is our voltage, and we're also given that. This is equal to 7,500 volts. And C is capacitance. We're not given information about this value. And here we have to get a little clever because we don't want to calculate for capacitance directly. We're actually interested instead in the charge on the capacitor. So it becomes important for us to redefine this capacitance term. Capacitance is equal to charge divided by voltage. And we want to replace this term with charge divided by voltage. Why? Because ultimately we want to solve for Q, which is charge. And the other variable present here, V, is a value we're given in the problem. So this is going to make our calculation a lot easier. When we replace this term, we get the following equation. U is equal to 1/2 Q divided by V multiplied by V squared. And here we get rid of one V term, and U is now equal to 1/2 QV. We want to solve for charge, so let's rearrange this equation to solve for Q. Q is equal to 2U divided by V. We have both of those values, so let's plug them in. U is 400 joules, and V is equal to 7,500 volts. Now 2 times 400, that's equal to 800 joules. And I'm going to approximate this value, 7,500, to just 8,000. This is going to make our math a lot easier. Here we get rid of these two zeros. Now we have 8 over 80. This simplifies to 1 over 10, and 1 over 10 is equal to 0.1. So our charge on the capacitor is equal to 0.1 coulombs. We can alternatively write this as 1.0 times 10 to the minus 1 coulombs, and this best corresponds with answer choice C. So the correct answer for problem 10 is C. Beautiful. Moving on to problem 11. Problem 11 says, a 10 ohm resistor carries a current that varies as a function of time as shown. How much energy has been dissipated by the resistor after 5 seconds? Now, power is defined as energy dissipated per unit time. If we are solving for energy, we can rearrange this equation to say that energy dissipated is equal to power multiplied by change in time. Now, in this 5-second interval during which the resistor is active, it has 2 ampere current for 3 of those seconds. That's important because we can redefine this power term. Power is equal to current squared multiplied by resistance. And if we plug this in for power in our energy equation, we get that energy is equal to current squared multiplied by resistance multiplied by change in time. And we have all 3 of those variables, so we can plug them in and calculate for energy. For current, we have 2 amperes, and this is squared. For resistance, we have 10 ohms, and for time, we have 3 seconds. 2 squared is equal to 4. This is multiplied by 10, that gives us 40, and then 40 is multiplied by 3, and that is equal to 120. So the energy that's been dissipated by the resistor after 5 seconds, that's equal to 120 joules. And you have to be really careful here with the change in time. I know it says 5 seconds, but it's off for 2 of those seconds. So you have to account for that. And so the correct answer for problem 11 is answer choice C. Next up, we have problem 12. Problem 12 says, in the figure below, 6 currents meet at point P. What is the magnitude and direction of the current between points P and X? In order to solve this problem, we need to recall Kirchhoff's current law. This law states that the algebraic sum of currents entering and leaving a junction must be 0. In other words, the sum of all currents directed into a point, that's always equal to the sum of all the currents directed out of the point. So we need to figure out the currents directed into point P, and we need to figure out the currents directed out of point P, and we need to make sure that they are equal to each other. For the currents directed into point P, we have 8 amperes, 3 amperes, and 2 amperes for a total of 13 amperes directed towards point P. What about current directed out of point P. We have 6 amperes over here and 5 amperes over here for a total of 11 amperes directed away from point P. We need these values to be equal. And to ensure that, this branch right here from point P to point X, this needs to be 2 amperes directed away from point P. And that makes the correct answer choice A, 2 amperes towards X. So that is another way of stating away from point P. Let's move on to problem 13. Problem 13 says, which of the following will most likely increase the electric field between the plates of a parallel plate capacitor? Before we work through each of the answer choices, I want to remind you that a parallel plate capacitor consists of 2 metal plates separated by a small gap that's often filled with air or another dielectric material. When a voltage is applied across the plates, an electric field is generated between them, and the electric field strength is given by this equation, V divided by D, where V is the potential difference or voltage across the plates, and D is the distance between the plates. From this equation, it's clear that the electric field strength increases with higher voltage and decreases with greater plate separation. So keep that in mind as we work through each of our answer choices. A says adding a resistor that is connected to the capacitor in series. Adding a resistor in series with the capacitor would not directly affect the electric field between the plates. Resistors do not increase the voltage applied to the capacitor, but rather they limit the current in the circuit. Since the electric field depends on the voltage applied across the plates and not on the resistance, this option is not going to increase the electric field. Answer choice B says adding a resistor that is connected to the capacitor in parallel. Again, connecting a resistor in parallel with the capacitor does not increase the electric field between the plates. In fact, it could cause some of the current to bypass the capacitor, reducing the effective charge that's stored on the plates over time. Since the electric field strength depends on the voltage, which remains unchanged by the resistor in parallel, again, this option will also not increase the electric field. So answer choice B is incorrect. Answer choice C says increasing the distance between the plates. If we increase the distance between the plates, then the denominator in the electric field equation, that's going to increase, meaning that the electric field strength decreases. Therefore, increasing the plate separation will actually reduce the electric field between the plates and not increase them. So answer choice C is also incorrect. D says adding an extra battery to the system. So batteries provide potential difference or voltage. If we connect an additional battery in series with the existing one, the total voltage applied across the capacitor will increase. Since the electric field is directly proportional to the applied voltage, increasing the voltage will directly increase the electric field between the plates. And so this answer choice is actually the correct one. 13 is D. Moving on to problem 14. Problem 14 says each of the resistors shown carries an individual resistance of 4 ohms. Assuming negligible resistance in the wire, what is the overall resistance of the circuit? Looking at this circuit, we have 2 branches that are in parallel. In this branch, we have 3 resistors in series, so we can easily calculate the resistance of this first branch by summing up the resistance of each resistor. 4 plus 4 plus 4, that gives us 12 ohms. In this second branch, we only have 1 resistor, and we know that every resistor in this circuit has a resistance of 4 ohms. Now that we have the resistance of each of these branches, we know that these branches are in parallel, so we can use the equation for parallel resistors to calculate the total resistance. 1 over the total resistance, that's going to be equal to 1 over R1 plus 1 over R2. This is going to be equal to 1 over 12 plus 1 over 4. Let's rewrite this so that we can easily sum up these two fractions. This is going to be equal to 1 over 12 plus 3 over 12. This gives us 4 over 12. 4 over 12 is equal to 1 over the resistance. Then we could take the reciprocal of both sides, and we get that the total resistance is equal to 12 divided by 4, which is equal to 3 ohms, and that corresponds with answer choice D. So problem 14 is D. And now we can move into our last and final problem. Problem 15 says, which of the following best characterizes the ideal voltmeter and the ideal ammeter? A says ideal voltmeters and ammeters have infinite resistance. B says the ideal voltmeter and ammeter have no resistance. C says ideal voltmeters have infinite resistance and ideal ammeters have no resistance. And answer choice D says ideal voltmeters have no resistance and ideal ammeters have infinite resistance. Let's go over the role of a voltmeter versus the role of an ammeter. A voltmeter is used to measure the potential difference between 2 points in a circuit. For the voltmeter to give an accurate reading, it has to draw as little current as possible from the circuit. If a voltmeter were to draw significant current, it would alter the voltage across the component being measured, and that would give us an inaccurate result. So to ensure that the voltmeter doesn't interfere with the circuit's behavior, an ideal voltmeter is designed with infinite resistance. With infinite resistance, the voltmeter becomes an open circuit, meaning no current can flow through it, and this ensures that the voltage across the component remains unaffected by the presence of the voltmeter. An ammeter, that's used to measure the current flowing through a particular part of a circuit. For the ammeter to measure the current accurately, it must allow all of the current to pass through it without adding any significant resistance. If the ammeter had any noticeable resistance, it would reduce the current flowing through the branch, and that would alter the circuit's behavior and give an incorrect reading. So to avoid this, an ideal ammeter is designed with zero resistance. And with zero resistance, the ammeter acts like a perfect conductor, allowing the current to flow through the circuit unimpeded. Keeping that in mind, ideal voltmeters then have infinite resistance, and ideal ammeters have no resistance, and that makes the correct answer for problem 15, answer choice C. And with that, we've completed our practice problem set. I hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.